Today we're going to be discussing section 5.2 on exponential functions and graphs. So our objectives today are to graph exponential equations and their functions, and then solve some applied problems involving exponential functions. The function f of x equals a to the x, where x is a real number and x is still our input here, is called an exponential function. So clearly our base is a. A is typically a number that is like 2 or 3 or 1/2. We set the base, and then x is where we still input different numbers. Remember, with functions, we want to be able to give an input and get an output. And so with these, our input is still x, but x is actually in an exponent spot. So when we're plugging into the exponent, that's what makes it an exponential function. Now, we do require the base a to be a positive number. That way we can avoid some imaginary numbers that we don't want to be looking at in this course. So some examples here are f of x equals 2 to the x, f of x is 1/2 to the x, or f of x is a decimal like 3.57 to the x minus 2. See, we can have some other operations happening up in the exponent as well. So let's start off with a quick example. Graph the exponential function of y equals f of x, which is 2 to the x. So if we have 2 to the x, and I plug in x equals -3, then I'm looking at 2 to the -3, which hopefully you practiced your worksheet problems today. That's 1/2 cubed, which is 1/8. That's about 0.125. That'll make it helpful for actually putting it on the graph. Now looking at f of -2, that's 2 to the -2. Remember, I just plug in -2 in place of x. Well, that's 1/2 squared, which of course is 1/4, which has a decimal 0.25. With the next one, we have 2 to the -1. That's, of course, 1/2, which is 0.5. The next one, we have 2 to the 0, and we know anything to the 0 power is 1. And then we have 2 to the 1. Well, that's just 2. 2 squared, that's, of course, just 4. And 2 cubed, well, that's 8. So now we have a bunch of xy points. We can plot them on the graph and find our actual function. So we have -3, 0.125, so that's going to sit -3 and just above the axis there. Then we have -2 and 0.25. That'll be just above the previous point. Now we have -1 and 0.5. Again, just a little bit higher we've gone. Now we have 0, 1. So we plot that point, 0, 1. Then we have 1, 2, so we plot that here. Now we have 2, 4, so that's starting to increase here. And we have 3, 8, which goes up here. So you can really start to see how this function is going to keep growing and growing and growing up as we keep going. And so, of course, it's going to come up along like this. And there we've graphed our function. They typically have this kind of curve where one side is going to fade away to 0 and the other side is going to shoot up to infinity. We just plot a few points to see exactly where those sit. Let's do another example, and this one's super similar to the last one. But here we want to note that 1/2 to the x, well, that's the same thing as 2 to the -1 to the x, right? We can use our negative exponent rule and bring that 2 out of our denominator here. Well, that means that here we just have 2 to the -x. And that's actually going to be something a little bit easier to plug into rather than dealing with powers of 1/2 over and over again. So now if we try to plug in -3, we think about f of -3, we're looking at 2 to the -3. Which of course is just 2 to the 3, which is 8. So we have 8 over here. Now f of -2, well, that's 2 to the -2, because I'm plugging in -2 in place of x. We can't drop the negative that's in front of the x already. Well, this one, of course, is just 2 squared, so that's 4. Now we have f of negative 1. That's 2 to the negative 1, which, of course, is just 2 to the 1, which is 2. F of 0, well, of course, that's 2 to the 0, which is just 1. Oh, I got to fill these in on the right still. 2 and 1. Now let's look at f of 1. We have 2 to the negative 1, right? We've plugged in 1 to 2 to the minus x. Well, that's just 1 over 2. So that's 0.5. Now, f of 2 is 2 to the minus 2. Again, just plugging in 2 for x. And that's 1 over 2 squared. Remember the negative exponent, we bring it down into a denominator, and that, of course, is just 1/4, which is 0.25. Lastly, we have f of 3. That's 2 to the negative 3, which is 1 over 2 cubed, 1 over 8. That's 0.125. So interestingly, here, as soon as we looked at 2 to the minus x instead of 2 to the x, our table sort of flipped. What we had before for 3, we're now getting for a minus 3. So this is what we call a reflection of y equals 2 to the x across the y-axis. And we've seen these before, right? Any reflection we want to do across the y-axis, we replace x with negative x. And so that's exactly what's happening here. In fact, throughout this section, you'll see a lot of our translation rules apply still. So let's graph this. So we have our graph on the left. All those points that we just solved, we have in our table. Let's plot each of those. We have negative 3, 8, negative 2, 4, negative 1, 2, 0, 1, 1, 0.5, 2, 0.25, and 3, 0.125. So here you can see we flipped across the y-axis from what we had before, and we start up at the top and slowly go down towards 0. So there we have graphed this exponential function. Now, in general, looking at our exponential functions, here's what can happen. When our base a is greater than 1, so this is our base a greater than 1 over here, you see that we actually grow. And the speed at which we grow depends on how large our base is. So for something like f of x equals 4 to the x, that grows much, much quicker than something like f of x equals 1.8 to the x. As in, it's a steeper curve, and it grows positively towards infinity. Now, on the other hand, when we have a base a less than 1, we actually see our function decline. It starts off really large, and it goes down towards 0. Remember the fact that whenever you have fractions, and you look at a list of fractions, as the denominator gets bigger, the overall fraction gets smaller. So as we start to look at powers of fractions, they quickly go down to 0. So that's what you want to look for here. Is my base a greater than 1, or is my base a truly a fraction that's less than 1? That'll tell us if we're increasing up to infinity or decreasing down to 0. So now let's look at a bunch of these graphs, and remember that we have a technique for looking at their transformations, which means I don't have to do the points and replot them every time. I know what 2 to the x looks like now. We've drawn it a couple times. And so we can just use what you know about our transformations to be able to graph the rest of these. So let's identify each of these transformations, and then we'll be able to graph them. I'll leave the graphing up to you guys, and we'll just write down what's happening here. So with part A, we have g of x equals 2 to the x plus 1. Remember that when we add 1 directly to the x, that is going to be a horizontal move. We either go left or we go right. And with horizontals, it's opposite the direction you want it to be. So we look at x plus 1 and we imagine that it's going to go to the right one. but that's not true. It actually goes to the left one. So horizontals are opposite how you kind of naturally imagine them going. So if we add 1 to x, we actually shift the graph left 1 unit. And that's because we added 1 to the x, we shift the graph left 1 unit. The 2 here, remember, is our base, right? So it was 2 to the x that became 2 to the x plus 1. So there's no vertical or horizontal shrinking or stretching happening here. Now let's move on to part B. We see we have 2 to the minus x plus 4. So that minus x we've already seen once today. That is a reflection over our y-axis. And it's also a vertical shift of a plus 4. So when we add something that's not in the exponent with the x, it's kind of on the tail end. That's when we know it's a vertical shift. Four units up. So it's a vertical shift and it's been reflected over the y-axis. Now let's look at the next one. There's a lot more going on here. We have a 3 minus, so we know that we've done a vertical shift up by 3, and we put a minus in front of the 2. That minus in front of the 2 means we've negated the whole function, and so this is really going to be, so the vertical shift 3 units up, and that's because of this guy. We also see a reflection over the x-axis because of this negative. We also see 2 to the 1 minus x. So there we've added 1 in our exponent, right? It's 1 minus x, but it's really negative x plus 1. It's the same thing. A little bit easier to see there, we've actually shifted to the left 1 unit. So we've shifted left 1 unit. And then see, x has become negative. That tells me we're reflected over the y-axis. So that's 1, 2, 3, 4 different transformations done on this one. And let's double check, right? We have the shift up from here. We have the reflection from this negative. We have the reflection from this other negative. And we have a shift from the plus 1. And those are all the operations that were done to the original function 2 to the x. So we know we've picked up all of the different transformations that have happened. All right, let's move on to the last one. We have a lot of the same ideas, but now we have that 5 out in the very front. When that 5 is out in the very front, not up with the x, but the very front, that tells me it's a vertical stretch by 5. We know it's a vertical because it's out in the very front, not up with the x. And then we know it's a stretch because vertical increases with a number greater than 1, and it would have shrank if that 5 were something less than 1. So this is a vertical stretch by 5. We know we've also shifted it up by really 5 units. Notice we actually need to distribute this 5. So let's write that down. It's 5 minus 5 times 2 to the x. So it's really been a vertical shift of 5 units up. And then, so that's the first one, that's the second one. We also have a minus in front of the 2. So, or a minus in front of the 5, that's in front of the 2, basically. Well, that is a reflection over the y, or the x-axis. Whenever we put a negative in the very front, we flipped from the top half of the graph to the bottom half. So we flipped over the x-axis, essentially. And those are the three operations I see happening to 2 to the x. So we've got all of the different transformations here. So there's a bunch of these on your homework about different exponential functions. They give you a base and say what happened, essentially. And so you have to pick up some of the same things we looked at. I think this was chapter 2 or 3, somewhere in there. Now, here's a little bit of a different problem type. This is on your homework, and I find it somewhat interesting. Let's look at when does 2 to the x plus 3 to the x equal x squared plus x cubed? So notice these are two very different functions, right? I have 2 to the x versus x squared. So in one side, my base is 2, and x is what I'm inputting into. And on the other side, x is my base, so that's what I'm plugging into, and any of those numbers get squared. So those are two very different functions. Of course, the same thing's happening with 3 to the x and x cubed. But if we wanted to know where they're equal, then we're going to plot y1 equals 2 to the x plus 3 to the x. And we're going to plot y2 equals x squared plus x cubed. Now let's go to our graphing calculator and see what this looks like. We want to go and plot 2 raised to the x plus 3 raised to the x, enter, and then we want to plot x squared plus x raised to the third, enter. When we look at this graph, it's kind of hard to see where the intersection points are. So you would have to play around with the window a little bit here. When we zoom out and we reset our window, we'll be able to see it a little bit better. So let's go from 0 to around 3.5. And then we'll go from 0 till about 50 and go by 5. Let's see what that looks like. Now we can start to see the intersections happening. It's still a little bit small. Maybe I can zoom in for you. But you can see a intersection point right in here and another one right in here. And so what you want to do is second, calculate. We go down to intersect, and I hit enter. It says, oh, well, where is the first curve? And so I can say enter, and it says, where is the second curve? And I hit enter one more time, and then I get my first intersection point. Now, if I'd scrolled all the way to the right, I would have gotten the right intersection point. So that's how we can solve. We get x equals 2.29. Now back to our slides. Here's a better picture of the graph where you can really see where those two intersection points are. We got 2.29. If we kept going, we would have gotten 3.23 on the other point. And so our x values are 2.29 and 3. We'll say x equals 3.23. Those are the two x values where this is true. You do have this problem on your homework, so I suggest practicing it, making sure you're using your calculator. Desmos is a really great tool here because you can really play around with the screen a lot and your different window sizes. So, take your time making sure that you can see where the intersection points are, but otherwise, we have figured out exactly where 2 to the x plus 3 to the x equals x squared plus x cubed. Now let's get into some applications of exponential functions. So here we have the total number of public electric charging units available for hybrid vehicles has increased exponentially since 2006. Number of outlets at these stations in T years after 2006 can be approximated by this function A of T. How many outlets were available in 2008 and in 2010? So note that the T represents the years after 2006. So if I want to see in 2008, I'm looking at T equals 2 because 2008 is 2 years since 2006. So now I'm looking at A of 2, which is just 228 times 2.22 to the 2. And we'll put this in our calculator to see what this looks like. So that was 228 times 2.22 raised to the 2. And we get 1,123.68. So let's go back to our graph. We have 1,000, oops. It was 1,123.68. And that is how many outlets were available in 2008. Now in 2010, we're looking at t equals 4, since it's 4 years since 2006. So we plug it in. Let's find a of 4. And we have 228 times 2.22 to the 4, which, going back to our calculator, is 228 times 2.22 raised to the 4. 5537.92. Back to the slides. 5537.92. That's how many outlets we had in 2010. So notice it grew quite a bit in just 2 years. That is what our numbers are going to look like anytime we have an exponential function. You will see your y values grow much, much quicker than our standard kind of linear quadratic functions. Now let's go into probably our most famous application of one of the most famous, I won't say the most famous, one of the most famous applications of exponential functions, and that's our interest formula. See, this formula tells us if I put in a principal amount of money into an account, and it has an interest rate R, and it compounds at a certain number of times per year. So if it's daily, that would be 365 times. If it is quarterly, that would be 4 times a year. You could have bi-weekly, which is going to be 52/2 times a year. You know, we can compound at different times per year, and they'll have to be given in the problem. But once we have all those details, the principal, the rate, and the number of times is compounded, we can plug in a time and know the value of our account at any time, essentially. So this P is our principal, R is our rate, the N is the number of times per year, again, daily meaning 365. We have quarterly, which means N equals 4. So you'll see different values like that. We'll need to pick up exactly what your N value is. And then T is our input. So we'll be able to input time and get a value of the account at that time. Remember, savings accounts and different investment accounts actually gain interest throughout the year. And so this gives us that calculation. So let's see an example. Suppose that $100,000 is invested at 6.5% interest, compounded semi-annually. Find a function for the amount of which the investment grows after t years, graph the function, and then we're going to find the amount of money in the account at t equals 0, 4, 8, and 10 years. And we're also going to answer when will the account reach 400,000. So we need our formula. We have A equals P parentheses 1 plus, it's R over N to the NT. And I'm just going to double check that I have that correctly. The R over N, yeah, it goes R over N, so that's perfect. R over N to the NT. Okay, so this is our function. Let's try to write it down now. So from the problem, we were given the principal amount of 100,000. We were given 6.5% annually, which we need to write as 0.065. And then we were told semi-annually, which means N equals 2. And now we just plug in these parts of the formula. A of t equals 100,000 times 1 plus 0.065 over 2 to the 2t. And that's our function. We could simplify it more. We really don't have to, though. We could simplify the 1 plus 0.065 over 2, but it's not really necessary at this step. Moving on to part B, we're going to use a graphing calculator with this specific viewing window, and we're going to look at what this function is. So let's keep it in mind, 100,000 times 1 plus 0.065 over 2 to the 2t. Let's work on plugging this into a calculator together. Clear this out. And we had 100,000 parentheses 1 plus 0.065 divided by 2 raised to the 2. Now, of course, instead of t, we use x. So notice that on this calculator, my 2x entirely ended up in the exponent. If you have a TI-83, which is one generation older than this calculator, you need to put that 2x in parentheses. If you see the caret button, this button right in here, if you see this button right in here in your text up here, that means you're going to want to put the 2x in parentheses. All right, some calculators won't automatically put it up in the parentheses like that. So let's look at the graph. However, this is still a strange viewing window. This problem told us to instead put the viewing window at 0 to 30 and 0 to 500,000. So in this window, 0 to 30 will count by 5, and 0 to 500, 1, 2, 3,000. And we'll count by 10,000. I don't want to see 500,000 tick marks on my scale. Maybe we'll go by 100,000. All right, look at the graph. And there's something we can actually see what our function looks like. Now, of course, we also have table values, so I don't have to plug in different t values. I can just immediately pick them up from my table. So we graphed our function. We've seen part B. Let's go back to our slides. So we saw on our graphing calculator with the specific viewing window, and we saw how to set that. Now compute a of t at t equals 0, 4, 8, and 10. And those are all on our graphing calculator. Notice on our table, we have zeros at 100,000, 4 is at 129,000, 8 is at 166,000, and 10 is at 189,000. So now, we could write all of those down. I'll let you do that on your own time. Now we're actually going to work on setting 100,000 equal to, 100,000 times our function to the 2t equal to 400,000. And let's solve using the calculator. This would be somewhat tricky to solve by hand. We don't have enough methods for solving it by hand yet, so we have to use the calculator. And what you're going to do is plot y1 equals our function, and then we're going to also plot y2 equals 400,000. Then we can use our intersection method and actually solve for our t value. So at what time is this account going to reach 400,000? That's what we're answering here. Let's go to our calculator. And I could scroll and sit here, and I know that the answer is going to be somewhere between 21 and 22. I can see that here on the calculator. That's around when we hit 400,000. But let's get it perfect. So we've already graphed our function. Now we're going to graph 400,000. 1, 2, 3, 4, 5. And on the graph, you can see the point where it crosses. Perfect. So now, second, calculate, and I go down to my intersection. Say, hey, where do these two things intersect? It asks me for the first curve, I hit enter. It asks for the second curve, I hit enter. I hit enter one more time, and there's our intersection, 21.67. So after 21 years, this function will be at, or excuse me, this account will be at 400,000. So 21.67. So T equals 21.67 years. No extra algebra, no extra math. We just had to plot the two things where we want to see where they're equal, solve for their intersection. All right, moving on. We're going to talk about a very special number that's called the number E. E is special for a lot of different reasons. You'll see kind of as you go on through mathematics, you'll see it pop up very interestingly in nature and populations. It's a very particular number. It doesn't terminate or repeat. It's irrational. Just like how pi goes on and on and on forever, E is the same idea. It goes on and on forever. And Euler is the one who discovered it, I suppose. So that's what we're talking about next. It's approximately 2.718. It is actually a button on your calculator, the number E, and we're going to practice with it here in a moment. So find each value of e to the x to 4 decimal places, and of course we're going to use a calculator. So e to the third, e to the 0, e to the minus 0.23, and e to the minus 2. Going to our calculator, clear this out. And on our calculator, you see right over here, there's ln, which means natural log, and above that in blue is e to the x. So that's the E button you want to be working with. And anytime it's in blue, we have to hit second first in order to access it. So if I hit second, E, you can see it's ready for me to type in an exponent. And the first one we were looking for is e to the third. So we get 20.0855. So I'm going to write that down on our slide, 20.0855. Now the next one is e to the negative 0.23. Here we get 0.7945. The next one then is e to the 0. E to the 0, we shouldn't even need to type in the calculator, but we'll do it together. Remember, anything to the 0 power is 1. So e to the 0 is 1. And the last one we were asked for is e to the minus 2. So I just type e minus 2, enter 0.1353. So now I'll go back to our slides. I have been writing these down, even though you couldn't see them. And we filled in our decimal places. Make sure you round correctly, especially on homework. There's 1 or 2 of these, but it's just a button on your calculator. You just have to plug in the exponent. So it's pre-programmed. It knows tons and tons of decimal places of E, and that's what it uses here. Now, as a function, it's still an exponential function. So looking at our f of x equals e to the x, you can see it grows up towards positive infinity. And e being about 2.7, that kind of makes sense. It's our base that is greater than 1, and so it should shoot up to infinity. And as soon as we put a minus in front of that x, we've reflected it over the y-axis. Therefore, it now goes down towards 0 rather than up towards positive infinity. This essentially becomes 1 over e to the x. So it's growing as a fraction, and as my denominator in a fraction grows, the overall value goes down. So that's why that e to the minus x actually goes to 0. But it's the same idea as before. It's still an exponential function. It still has its own translations and transformations that we can pick up. So let's start here. We will graph f of x equals x to the e to the x plus 3. We'll plug in a few points and see what we get. So going to our graphing calculator, e to the x plus 3. And let's clear everything out. And my y equals needs to be cleared. I'm going to reset my window from negative 10 to 10. Negative 10 to 10. And a scale of 1. And graph, there's nothing there. All right, we are all cleared out. So let's look at that graph. I can type e here to the x plus 3. So I can graph it just like I do any other function. I use e as a button on my calculator. I know it's about 2.7, and I type in x plus 3 as the exponent. When we look at the graph, there you can see it. And we have a table. We can see all of the values on my table. Negative 3, negative 2, negative 1, 0, 1, 2. And actually pretty quickly, my table is going to go off the map as soon as we get to 0. So we have negative 3, 1, negative 2, 2.7. 2.7. And negative 1 is at 7.4. And 0 is at 20.1. So we can put a couple of these on our graph and see what our function is going to look like. I know I have now negative 3, 1. I have negative 2, 2.7. I have negative 1, 7.4. And I know then, because we've seen this function before, that it's going to swoop from the axis like this and shoot up like this. Also notice e to the x plus 3, well, that's a shift left by 3 units coming from e to the x. So we look at e to the x and we shift it left 3 units, we're looking at this type of function. So starting from what we know about e to the x makes it really helpful because we see points for e to the x. We know what e to the x looks like. And this graph is simply e to the x shifted left 3 units. Let's do another one. Now this time I have e to the minus 0.5x. And so this is going to be a reflection across. Now, is it the x-axis or the y-axis? Well, we put the negative in front of the x, so we have flipped across the y-axis. We also see we have a 0.5 in front of the x. It's directly in front of the x, so we know it's a horizontal stretch or shrink. And we know it's a horizontal stretch because the 0.5 is less than 1. So this is a horizontal stretch by 0.5. So we should see it be a little bit more steep than before. A horizontal stretch. Actually, I think we're going to see it be a little less steep. For stretching it horizontally, it's going to take a little bit longer for it to grow, essentially. And then, of course, reflected across the y-axis, so it's actually going to go down towards 0 instead of up towards infinity. So let's look at this graph on our calculator, e to the minus 0.5x. We go to our y equals, and I have second, there's e to the negative 0.5x. And I go to the graph, and there we see it is a little bit more leveled out than before. It's not quite as steep, and it does go down towards 0. So if I go to my table, at negative 3, I'm at 4.4. Negative 3, I'm at 4.48. At negative 2, I'm at 2.7. At negative 1, I'm at 1.65. 0, of course, I have 1. And at 1, I have 0.6. 2, I have 0.36. 37 if I round properly. And at 3, one more, 0.22. So we have all our different points. We go back to our slides. And we've written down all these different points. So all we got to do is plot them and see what our function actually looks like. We should have an idea because we've seen the picture and we know what we did to e to the x to get to here. But let's plot the points anyways. I have -3, 4.48. -3, 4.48, somewhere in here. I have -2, 2.7. -1, 1.6. 0, 1. 1, 0.6. 2, 0.37. And 3, 0.22. And so now I just draw my line. I could go a few points back to the left if I wanted to be super accurate, but I'm sure it comes down somewhere like this and across our axis here. And so that's this function, e to the -0.5x. Now let's do one more. Here we have f of x equals 1 minus e to the -2x. So here, of course, we have a vertical shift of 1. Now I have a minus in front of the e and a minus in front of the 2x. So that's a reflection over both axes. So we've reflected over the x-axis and y-axis. Again, we have a minus in front of the e itself. That flips us over the x-axis. We have a minus in front of the 2x. That flips us over the y-axis. Now we also have a 2 in front of the x. It's directly in front of the x, so we know it's a horizontal shrink. By 2. Oops. Slides are giving me a little trouble. Shrink by 2. It won't let me draw. There we go. By 2. Horizontal shrink by 2. All right. So let's go to our calculator now. 1 minus e to the -2x. Y equals 1 minus e to the -2x. Notice I use a negative in front of the 2, okay? Not a minus symbol. So the minus symbol, anytime you're combining two terms, use the negative symbol if it's going directly in front of a number. And here's the graph. And now we look at our table and we copy these down onto our table on our slides. At -3, we're at -402. At -2, we're at -53. So we're going to skip those. At -1, we hit -6.4. At 0, we have 0. At 1, we have 0.86. And at 2, we have 0.98. At 3, we have 0.99. Really, that would round to 1. So we'll round it to 1 perfectly. All right, let's actually plot these points, see what our graph looks like on our slides. So -1, -6.4, 0, 0, 1, 8.6, 2, 0.98. 3 is basically at 1. So our function comes up just like this, and you know it's going to level out at 1. Before, it would have leveled out at 0. We've shifted up by 1, so I know this graph should never cross that line y equals 1. Let me say that one more time. Normally, our e to the x function does not cross the x-axis. So here, since it's vertically shifted 1, it's not going to cross the line y equals 1. So this is it for this function. We've identified its transformations from e to the x. We plotted a few points and was able to plot our graph, and it does match what we saw on our graphing calculator. So that's it for today's lecture. Please reach out to me if you have any questions, as always.